Hello, and welcome to the video lecture for topic 16, ethers and epoxides. Now, ethers, of which epoxides are a subclass, are formed from alcohols and alkyl halides by some type of a substitution reaction. For SN2 type alkyl halides, the alcohol is first deprotonated, right, and to form a good nucleophile and displaces the halide leaving group. So we can have here a generic alcohol. We typically deprotonate this using a strong, irreversible base like sodium hydride. Right, sodium hydride is going to go, its lone pair grabs that hydrogen, breaking the hydrogen-oxygen bond to give us our deprotonated alcohol, which is known as an alkoxide. I'm just using ethanol, for example, but really this can be any alcohol, primary, secondary, or tertiary. We also, which our counter ion for this is going to be that sodium ion. And here now we have also formed H2 gas. This is an acid-base equilibrium in theory. However, because H2 is a gas, it escapes from the reaction, right? Also, its pKa is so high that the probability of this being reversible is next to nothing. So if we're going to put an equilibrium arrow for there, that's the size of the reverse reaction we're going to go for. From here, right, our alcohol can now attack into any of our SN2 appropriate alkyl halides. So that's going to be our methyls, our primaries, or our secondaries. So here's our SN2 appropriate alkyl halide. And our alkoxide will approach from the opposite face, displacing our halogen to give us our ether, and our halide ion. It has a negative charge that has to be balanced, and so our sodium ion balances that out. And so that's one way that we can form alkyl halides via an overall SN2 type process. Now, in our SN1 type processes to form an ether, right, this is going to be very similar. However, we know that for our SN1 processes, these are going to be our tertiary and secondary alkyl halides. So in our first step, right, our halide dissociates to form our carbocation. Right, we have our halide to balance out that positive charge. And now in a second step, our alkoxide. And again, I'm just using any generic preformed negatively charged oxygen, is going to go ahead, not alkoxide yet. Sorry, for our SN1 processes, we form our carbocation, right? Our alcohol, which is a decent nucleophile, can bond to that carbocation. We've now formed our protonated oxonium, which can then be subsequently deprotonated by some sort of a mild base. So here now, I'm going to go ahead and leave my X minus. I really like pyridine for a mild base. We could also use triethylamine. Either of those is perfectly appropriate. And we get to our newly formed ether. So this is how we make ethers. And of course, our byproducts from this reaction, right, are protonated mild base with a positive charge and our halide anion to balance that out. So this is how we make ethers, which I wanted to get out of the way at the beginning so that we can actually do something a little bit more fun. One last word on this before we move into the reactions of ethers and epoxides, right, is that, or two more words I should say before we move into the reactions of ethers and epoxide, is here I've overall shown intermolecular processes to form acyclic open chain ethers, right? Intermolecular between two molecules, between an alkyl halide that is separate from an alcohol, right? We can go by SN2, we can go by SN1, and in both examples we ended with a acyclic ether, which is open chain. Now, this can also be an intramolecular process where my alkyl halide and my alcohol are all in the same molecule. The alkyl halide carbon and the molecule carbon are somehow connected together, right? We can still do either an SN1 or SN2 process to form an ether, except now we're going to form a cyclic ether. And you've seen cyclic ethers before. THF is a cyclic ether. It is a 5-membered ring. So here we have THF, right? This is simply a 5-membered ring. One of those is an oxygen atom, right? This is a cyclic ether which could be produced by an SN2 process, since both of these carbons are primary carbons. Now, we can also produce a very small cyclic ether. So this is THF. If we only have 2 carbons in that entire cycle, 2 carbons and 1 oxygen atom, so if we make an ether that looks like this, right, we have 1 oxygen atom and 2 carbon atoms in our cyclic system, and we can have all the substitution off of those 2 carbon atoms we want. This is the epoxide functional group. Right? And again, we can form epoxides through these same types of processes, right? This is just a cyclic ether as opposed to the 2 examples at the beginning, which are the open chain ethers. Okay, overall, this process of forming ethers under some sort of a basic condition is our second name reaction we're going to see in Chem 201. This is known as the Williamson ether synthesis. It is formally the reaction between an alcohol and an alkyl halide under basic conditions to form an ether. All right, so now that we've gotten the formation of ethers out of the way, I'm going to want to move on and talk about substitution reactions that ethers can participate in, followed by substitution reactions, or ring opening reactions, I should say, for epoxides. So now that we know how to make an ether or make an epoxide using a Williamson ether synthesis, the next thing we need to do is go on and look at how ethers behave in substitution reactions. Now, for this portion of the video lecture, the reactions that I'm going to show you are only applicable to open chain acyclic ethers or cyclic ethers that are not epoxides. The behavior of epoxides in substitution reactions is very unique. And so we're going to take a look at that separately at the very end of this video lecture. So when we're working with any non-epoxide ether and we want it to behave as a nucleophile in a substitution reaction, it needs to be activated in some way, similar to how we activated alcohols for substitution reactions. And so there are 2 ways by which we can activate an ether, right, activate any non-epoxide ether towards substitution. And the first of those is to use either hydrogen iodide or hydrogen bromide. So if I put up a relatively simple ether, just a moment. So here I'm going to put up a relatively simple ether. And we see that if we treat this ether with hydrogen iodide, and again what I'm showing here is also applicable if I were to use hydrogen bromide, the first step, the oxygen of the ether is going to behave as a base. It's going to pick up that hydrogen ion, a hydrogen atom from our acid to form an oxonium. And we're going to have iodide, or if I was using hydrogen bromide, we'd have bromide and ion, right, produced by this acid-base reaction. Now from here, we have two different types of carbons on this example ether that I've given. One is a, we have two types of carbons. I'm going to fix this up a little bit. Didn't quite draw what I intended. So we're going to change that ether here real quick. And we're going to make it a secondary on one side versus a primary on the other, whereas we had two primaries before. So now that I've got two different types of carbons on each side of this oxonium oxygen, right, we have to decide which of these two potentially electrophilic carbons, or which of these two electrophilic carbons is going to be the side that the iodide anion attacks at. And so we have to think back to our rules and our properties of SN1 and SN2 reactions. Now, SN1 reactions, we know that the rate determining step there is going to be formation of a carbocation, a unimolecular process. Whereas in SN2 reactions, we know that the rate determining step is when the nucleophile attacks the electrophile and displaces the leaving group, a bimolecular process. Unimolecular processes are always faster than bimolecular processes. And so that means SN1 is going to always be a faster reaction than SN2. Now within each of those reaction mechanisms, we know further that the nature of the electrophile also has an effect on the rate of reaction. And so we know that for SN1 reactions, benzylic electrophiles are faster than allylic electrophiles, which are faster than tertiary, which are faster than secondary. And we know that primary or methyl electrophiles can't be substituted by the SN1 mechanism. Further, we know for our SN2 reactions that our methyl electrophiles react faster than primary electrophiles, which will react faster than secondary electrophiles. So here now, in our oxonium, our activated ether, we have a secondary carbon and we have a primary carbon, right? In the absence of information regarding the solvent of this, primary versus secondary, we're going to go back to our SN2 chemistry. We're going to see that primary electrophiles react faster than secondary electrophiles. And so preferentially, our iodide will attack at that primary carbon, breaking the carbon-oxygen bond, and we will end up with a secondary alcohol and a primary alkyl halide. Now, this is just how to determine what our major products are going to be, right? So these two, our primary alkyl halide and our secondary alcohol, these are going to be our major products. That is not to say that our iodide can't attack at that secondary electrophilic carbon. In fact, it can. And so we have a slightly lower probability, but still a realistic expectation that our iodide will attack at that secondary carbon to give us a secondary alkyl halide So here now is our secondary alkyl halide and a primary alcohol. However, because secondary carbons are slower at SN2 chemistry than primary carbons, both of these products are going to be our minor products. So when we cleave an ether with either HI or with HBr, we have to be on the lookout for what are our major products, what are our minor products. We need to also be aware, right, that even though we have these differences in reactivity between SN1 and SN2, all potential probabilities, right, that relate to sp3 electrophilic carbons are going to happen. We just need to be able to determine which our major products are and our minor products are. Okay, I'm going to move on now to our second method of cleaving ethers, right, activating and cleaving ethers in substitution reactions, which is going to be the use of trimethylsilyl iodide. So our second way to activate and cleave ethers is to use a reagent known as trimethylsilyl iodide. So I'm going to put information about it up over here. So trimethylsilyl iodide. Now this reagent is commonly abbreviated TMSI, and it has a structure that looks like this. We have a silicon atom that has 3 methyl groups and an iodide bonded to it. Now, what we're going to see here in a second is that silicon can serve as an electrophile for SN2 reactions, even though it has 3 alkyl groups off of it. And the reason that silicon can do this where carbon cannot is because silicon is actually physically larger than carbon. And so it has more room around it to spread out the 5 groups in the SN2 transition state, and the potential energy barrier to get to that transition state is sufficiently low enough that we can do SN2 reactions on a silicon atom, even though it is fully substituted, where we can't do that on a carbon atom. There's just not enough room, carbon's just not big enough to be able to accommodate the transition state. So in the first step of cleaving an ether with TMS iodide, we're going to have oxygen act as a nucleophile. It's going to attack into that silicon atom, SN2 style, to liberate an iodide anion. And so now we have our oxonium species. Again, this is an oxygen atom with 3 bonds to it, 1 lone pair, positive charge. And so here now we have our oxonium, right? We also have generated a iodine anion, which can now serve as an electrophile in a second step. And what we talked about earlier with HI and HBr activation of ethers still holds true. We need to remember that SN1 will be faster than SN2, and that when we're comparing within each of those, we have to remember the order of reactivity for our electrophiles. I'm using the same starting ether, so we're going to have the same overall reactivity, but let's take a look now at what those products from using iodide, from using TMS iodide versus using HI or HBr look like. And so again, iodine will preferentially react with that primary electrophile. Our major products are going to be a secondary molecule that has oxygen still bonded to silicon, which has those 3 methyl groups on it, right? Because we did not use a proton to activate our ether, right, we don't form an alcohol. Here what we formed is known as a silyl ether. We've also formed that same primary alkyl halide from our previous example. So these are going to be our major products. But just like we saw when using HI or HBr, the potential for our nucleophile, our iodine, to attack at the other carbon still exists. And so we will see some product forming from the iodine, attacking into that secondary carbon now instead. And we're going to get a different set of molecules as our minor products. This time, we're going to form a primary silylether and a secondary alkyl halide. Right? And so now these two are going to be our minor products. Okay, so now we've seen two different ways that we can activate ethers, right? And these are going to be our cyclic ethers that are not epoxides or any acyclic ethers towards substitution reactions, right? We've seen how to use HI or HBr, and we've also seen how to use TMS iodide to affect these kinds of transformations. All right, from here, all that's left for us to do is to talk about these ring opening substitution reactions of epoxides, which we'll do in the last portion of this video lecture. Now, epoxides are a very special type of cyclic ether. If we take a look at our epoxide, we see that it is very, very similar to a cyclopropane. We have 3 atoms forming a 3-membered ring, except the only difference between a cyclopropane and an epoxide is that one of the atoms of that ring is an oxygen. And a lot of the properties that are true about cyclopropanes are also true for epoxides. The most important of those properties being that epoxides have a lot of ring strain in them, right? These 3-membered rings, we have to have these banana bendy sigma bonds, which are very weak, right? Either that or we have a high degree of angle strain. One way or another, this ring is very strained, it has a very high potential energy, and it wants to open up and relieve all of that ring strain. So epoxides are the only ether we're going to interact with that does not need activation in order to undergo a substitution reaction. We can consider that it is already activated by the fact of its extremely high ring strain that it has. That very high strain energy in the molecule, right, means that this system is ready to undergo reaction pretty much at the drop of a hat. And so one of the interesting features is that this is one of the few times we're going to see O-, a strong base, able to act as a leaving group. And the reason that it can do that is because when we open up that ring and generate our O-, whether this is through an SN1 type pathway or an SN2 type pathway, we relieve so much ring strain that it's actually more favorable to have a strong base as a leaving group than to leave the epoxide in its cyclic form. Okay, so let's take a look at a couple of reactions, right? A couple of different ways that epoxides can react. Now, most often, epoxides are opened up by SN2 type reactions. And so for SN2 type reactions to happen, we need to have either primary or secondary carbons, which means I'm going to go ahead and change these two R groups to be hydrogen atoms. So here now I have this secondary type electrophile, right? This carbon, both of these carbon-oxygen bonds are polarized towards the oxygen, making both of those carbons electrophilic. But here now I have a tertiary carbon on one side and a secondary carbon on the other. That secondary carbon under SN2 conditions, right, SN2 mechanism conditions, is going to preferentially react with an electrophile, react with a nucleophile. So here now I'm going to bring in my nucleophile. It's a Lewis base, so it has a lone pair. That nucleophile is going to attack at my secondary carbon. We'll draw a nice clean arrow. That's going to break this carbon-oxygen bond, which is polarized and weaker than our carbon-carbon bond, O minus is going to end up being my leaving group, but that's okay because I've relieved so much ring strain that the molecule's potential energy is so low that it's fine dealing with having a strong base as a leaving group. So we see here now, we've eliminated that ring strain. Our negatively charged intermediate can and will adopt 109-degree bond angles. We don't have to bend any of those sigma bonds in any way. This is a much more stable scenario than having, or a much lower potential energy scenario than having our epoxides still in a cyclic structure. And our final step is that we have some sort of mild acid source. I'm just going to call this HA and mention that it is a mild acid, which our strong base can be protonated from to give our final product. Which is an alcohol of some sort. Now, at the beginning I mentioned that this is for SN2 type processes, right? And SN2 type processes typically happen under basic conditions. That's what we see most frequently, and that's what we're typically going to see in Chem 201. And so under these basic conditions, first we have nucleophilic attack at the less substituted carbon, which results in ring opening. Finally, in a second step of our reaction mechanism, we have protonation of that alkoxide to give our ring opened product from our substituted and ring open product from our epoxide. Now, the second scenario that we can see would be under acidic conditions, right? The second epoxide ring opening we're going to encounter is under acidic conditions. So under acidic conditions, and here now I'm going to have both of my carbons are technically, in my epoxide, are technically capable of going through an SN2 process. But here now, because I'm going to start off with some sort of acid and I'm just going to use halogen acid so that I have a built-in nucleophile, right? So the first thing that happens is that our oxygen is going to get protonated by that strong acid we have, right? And so now we have what I like to call potential for a pseudo SN1, right? We're going to see that pseudo SN1 here in just a second. So now we have this protonated epoxide, and we have our bromide anion, which I'm going to conveniently use as a nucleophile. Now, both of these carbon-oxygen bonds are polarized. And because I've formed this oxonium, right, these bonds are weakened, right? That polarization increases, and so these bonds are weakened. Excuse me, left a lone pair off of that oxygen. There we go. And a negative charge on my bromine. All right, so both of these carbon-oxygen bonds are now extremely polarized and weakened. And so I want to look at these, right, and see what it means for these to be weakened. So if I look at my secondary carbon to my oxygen and think of this as being weakened, as the one of the two bonds that could be weakened, I can think that as this is weakened and forming a partial bond, right, I can think that there's a delta plus at that secondary carbon. Alternately, we can imagine that potentially the oxygen carbon bond to that primary carbon could also be weakened, right? And so now what we need to evaluate is which of these two forms better stabilizes that partial positive. Is it better for me to have a partial positive charge on a secondary carbon? Or is it better for me to have a partial positive charge on a primary carbon? And it turns out, due to hyperconjugation and all of the principles we've seen before, that it's actually better to have that charge, right, that partial positive charge, start to develop on a secondary carbon. So this is better. And this is now why I call this a pseudo SN1 process, because the reaction doesn't actually proceed through an SN1 mechanism, but SN1 principles are at play here. And so what we'll see is that our major product from this reaction will be our bromide, our major product from this reaction will be our bromide attacking into the secondary carbon. So this is going to be our major product pathway. And our minor product pathway will be from our bromide attacking at the primary carbon. So this is our minor pathway, which tells us that we will get two products. Our oxygen is already protonated, so we don't need to have a second protonation step under acidic conditions. Our major product, we have a bromide, secondary bromide, primary alcohol, and our minor product will have our secondary alcohol and our primary bromide. Now, I haven't shown stereochemistry in here because all of these reactions, whether it's going by a true a true SN2 pathway or a pseudo SN1 pathway, typically our major products are going to be result with inversion of stereochemistry at the carbon that's substituted, right? And you can take a real good look at this in Sorrel, right? You'll be able to see the stereochemical results a lot better, right? And so I would advise you go and take a look at, it is page 225 in Sorrel. Here now again, just to label it, this is our major product, and this is our minor product. Okay, so that's what I've got for you for topic 16, reactions of ethers and epoxides. Remember, we can activate ethers in one of two ways. We can use either HI or TMS iodide, which allows iodine to then serve as a nucleophile and open up those ethers, whether it's ether cleavage of acyclic ethers or ring opening of cyclic ethers. And we've seen now how epoxides react under true SN2 conditions or acidic, what I call pseudo SN1 type conditions. All right, so that's what I've got for you for topic 16. As always, if you have any questions, please feel free to bring those into lecture, conference, or stop by for office hours. Thank you very much.